Hi, I'm Fernando Pereira from UFMG, and today we shall see how we can do type inference via a system of constraints. We will explain how to do constraint generation and what's the meaning of each constraint. So, as a quick recap, we will be generating types in three phases. First, we generate the constraints, then we solve them, and finally, we annotate the program. The open variables in the program, with the solution of the constraint system. We'll be using the function gen to generate constraints. This function receives three arguments: a type environment that associates types with three variables, plus the expression e that must be processed, and tau, the type variable used to annotate e. This function returns a set k of constraints. The constraints, which we have not seen yet, relate type variables. Type variables are placeholders for concrete types. We will denote them with alphas and taus, but we will reserve tau for the types that are used as annotations in the program that we are analyzing. And the constraints are equivalences that relate type variables. In this figure, you have a conjunction of four constraints. The constraints will follow the syntax on the left. And in the end, we want to replace the open type variables with ground types. Ground types are types without open variables. Notice that our language supports parametric polymorphism, so we can have ground types with quantified variables. That's like having the for all within a type definition. The for all declares a variable, so that variable is not free in the body of the type. Ground types let us see type inference as the problem of replacing type annotations with them, so that the program type checks. As an example, we are replacing the blue type annotations on the top with these mappings in the solution table, and then we have the final program with variables annotated with ground types in red down the figure. Let's then implement the gen function. It will have a definition for each possible term in our toy extension of the lambda calculus. For instance, for constants, we generate an equivalence between the type of the constant and the input type annotation. I know it looks weird now, but bear with me. We will make that clearer later. And for booleans, we generate equivalences with bool. To produce a constraint for a variable, we check the type of that variable in the input environment. Then we produce an equivalence with this type. For abstractions, it's a bit more complicated. I will try to explain what's going on, but before that, could you try to stop the video and read this pattern over? We will get back into them. Let me give you easier material first, to pave the way to an explanation. So if you remember, whenever we visit a variable, we generate an equivalence for the type of that variable in the environment gamma. But then the type of the variable must be in gamma. How does it get there? Whenever we want to generate constraints for a type abstraction, we add the type of the lambda argument to the environment. So if we find this variable in the body of the lambda expression, that's the uppercase E in this figure, then the type will be there. Let's try to generate all the constraints to this program in the gray box. This example will help us to understand how constraint generation works. This tiny program here. So that's how we invoke gen on the example program. Notice that it starts with an empty environment. We also start constraint generation with a type variable tau0 here, meaning the type of the entire program. We will need these three rules to generate constraints for this program. Would you like to see which rule would be applied in which order? Our program is a lambda abstraction, so we start with the rule for lambda abstractions on the lower left side of the figure. This abstraction holds an addition, so we'll have to evaluate this addition with the upper rule. And this addition uses two variables, hence we will need to generate pattern for variables using the rule on the right side. And here you have the solutions for constraint generation in this case. I will not go over the generation steps, but you can try to write the derivation tree yourself for this program. Later on I will show derivation tree for another program. And before we see other constraint generation patterns, take a look into the constraints. Would you be able to solve them? Stop the video and try to solve these equivalences. Then check if your solution makes sense with the types that you would expect for the three type annotations in our target program. There is 3 because you also have to count tau 0. And here you have the gen function for applications. See how we invoke gen recursively over each part of the application and then build a conjunction of the resulting rules. So how do you think we could build gen for these 3 extra rules that we have in our toy lambda calculus? Here they are, the constraints for the extensions. Take a look into how we change the type annotation that is passed as third argument of the gen function each time. In short, these are the rules that we use to generate constraints for programs. You can see the gen function as a visitor, from the visitor design pattern, that goes over the abstract syntax tree of a lambda expression, producing constraints. As an example, let's generate constraints for this term up here. We start with an empty environment, so here's our empty environment, and have an initial type variable tau 0, which will be the type of the entire expression. This expression is an application, so we call the pattern of applications. That will force us to call 2 other patterns, one for each side of the application. For the constant, we generate immediately an equivalence with int. Then on the other side, we have another application. So we will have to perform 2 more recursive calls. And we will generate a new equivalence for another constant. And we will have an abstraction on the left side that will produce an equivalence. And then we will invoke gen again on the body of the lambda expression. So there will be gen being invoked again on the body of the lambda expression. An abstraction yields another equivalence, and we will invoke gen on the conditional expression. The pattern for the if-then-else causes to invoke 3 times the gen function. We will be invoking gen 3 times more for the less than operator. And we will need to generate constraints for the variables. Each one of these invocations generates a constraint. In the end, these are the constraints that we get. Challenge: can you stop the video and try to solve these constraints? We'll find the type of the program. You find the type of tau 0, it's the type of the program, plus the types of tau 1 and tau 2, which are the types of x and y.